Okay, shall we start? So today I'm gonna first briefly talk about the midterm. Problem number one, show that limit as n goes to infinity, 1 minus 1 over n to the n is equal to e to the minus 1. So I believe from your lecture notes, the professor showed that this is equal to e, right? So you just modify the proof a little bit, basically follow the same argument, you can show this. So I'm not gonna talk too much about that. And problem number two, so you want to show that if limit as n goes to infinity, as n is equal to s, then limit as n goes to infinity, s0 plus s1 plus all the way to sn over n plus 1 is equal to s. So basically, the idea is to break that into two parts. So first we have s0 plus s1 all the way up to s sub n plus s sub n plus 1 plus dot 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 Sn over n plus 1. Okay, so these can be very far from S, but there's only finitely many of them. So if you let n goes to infinity, this part goes to 0. And on this part, if you choose n big enough, then you can have all of these very close to S. So basically, it's almost like n minus n plus 1 of S over n plus 1. And you let n goes to infinity, that goes to S. So for the detail, so in fact, this is problem 14 from chapter 3. So I talk about this exact problem during discussion when it was still an in-person discussion. So go back to your notes and you can see the full solution. Okay, now for number 3, test the convergence for this series. Okay, so n factorial square over 2n factorial. Okay, so for this, we can use the ratio test. So we let this to be an, and this will then be n plus 1 factorial square over 2n plus 2 factorial times 2n factorial over n factorial square. So this is going to be, so for this, you can write it as n factorial square times n plus 1 square. Okay, so cancel with that. You have n plus 1 square on the numerator, and this is 2n factorial times 2n plus 1 times 2n plus 2. Okay, so cancel with that. You have 2n plus 1. So this is n plus 1 square. So you have 2n plus 1, 2n plus 2. Okay, limit as n goes to infinity. And so 2n plus 2, that's 2 times n plus 1, right? So you can cancel another n plus 1 with that. So that's limit as n goes to infinity, n plus 1 over 2 times 2n plus 1. So this limit goes to 1 over 4, okay, which is less than 1. So by the ratio test, this converges. So I graded this problem. Here's my marking scheme. So first, the correct setup for the ratio test. So basically this step, that's 4 points. Okay, correctly evaluate the limit, that's 4 points. Okay, and 2 points for the conclusion. Okay, so that's that. All right. So part B, sum n from 1 to infinity minus 1 to the n square root of n plus 1 minus square root of n minus 1. Okay, so as you can see, this is obviously an alternating series, right? So let's call this, say, Bn. So to apply the alternating series test, we need to show two things. So Bn is monotone, decreasing, and limit as n goes to infinity, Bn is equal to 0. Okay, so how do we do that? So this is the trick you've seen many times. So we can multiply by its conjugate. So that's n plus 1 plus n minus 1 over n plus 1 square root plus n minus 1 square root. Okay, so if you multiply things out, that's going to be 2 over n plus 1 plus square root of n minus 1. Okay, so this, how you take the limit, this obviously goes to 0, and it's obviously monotone, right? Because you increase n, you're increasing the denominator, so your sequence is decreasing. Okay, so some of you use calculus to show that it's monotone. So you define fx is equal to square root of x plus 1 minus square root of x minus 1. You take the derivative, you can show that the derivative is always negative. So that's decreasing. Okay, that's fine too, in my opinion. But the professor said it is essential that in this course you know the you know something about ordered field. So I just took 1 point off. Okay, so for number 4, radius of convergence. So sum from 0 to infinity n factorial over 2 to the n square z to the n. Okay, so how do we find the radius of convergence for this? Okay, so we can take the ratio of this. So let's call this an. So let's take the ratio. So what is that equal to? That's n plus 1 factorial over 2 to the n plus 1 square times 2 to the n square over n factorial. Okay. All right, so that's limit as n goes to infinity. N plus 1 factorial, that's n factorial times n plus 1. So cancels that. And this is essentially 2 to the n squared plus 2n plus 1. Okay, so what's left is n plus 1 over 2 to the 2n plus 1. And obviously that is going to 0, right? So the radius convergence is infinity. Okay, so I think everybody got this one correct. And part B, this is n equals to 0, infinity z to the n square 2 to the n. Okay, so this is a tricky one. Why is that? Because here the exponent for z is n square. Okay, so the series really, if you write it out, what that really means is, okay, so for n is equal to 0, you have 1 plus, Okay, 1 over 2 z plus, and next, if you plug in n is equal to 2 here, you have 2 squared, that's 4. So that's 0, z squared plus 0, z cubed plus z to the 4, 2 squared, that's 4, right? And then a bunch of zeros. And then when you get n is equal to 3, so that's z to the 9 over 8. Okay, so that's your series. Okay. All right. So some of you used root test. So to use the root test, it's important to not take the nth root, but n squared root. Okay, so if you want to use root test, so you have to take this z to the n square over 2 to the n 1 to the 1 over n square. So this has to be the inverse of that. Okay, so if you do this, you have z over 2 to the 1 over n, right? You take limit as n goes to infinity. So if you want this to be less than 1, then z has to be less than 1. The norm of z has to be less than 1. Okay, so if you take the nth root instead of the n squared root, I will take 3 points off. Okay, so same thing for the ratio test. If you use the ratio test, you have to be very careful because an plus 1 over an, one of them will be 0 if you look at that. Okay, so make sure to be extra careful. Okay, next, number 5. Number 5 is also very tricky. So we want to test the convergence of this series for every complex number. Okay, so it's important to know that you have to consider all the complex numbers, not just the real numbers. But the first step is the same. We take the ratio of the coefficients. So let Cn be 1 over square root of n plus 1 times n plus 2. So we look at the ratio. So that's limit as n goes to infinity. Okay, so these two cancel, and it's clear that it is 1, right? So your radius of convergence is 1. Okay, so you immediately know it's going to diverge for all the z whose norm is greater than 1, and converge for all z whose norm is less than 1. Now the problem is, what about on the boundary when the norm of z is equal to 1? Okay, so if you get this part right, so that means if you get the radius convergence right, you get 6 points. Okay, now for the boundary, what do we do? So first, you know that Cn is monotone, decreasing, okay? Then you use theorem 3.44 from your textbook. It tells you that the series will be convergent on the boundary, except possibly when the norm of z is equal to 1, or except possibly when z is equal to 1. Okay, then you have to check what happens when z is equal to 1. When z is equal to 1, here's what you get. You have sum 1 over root n plus 1 times root n plus 2, right? And then you can see this is greater than, so from 0 to infinity, right? So that's greater than or equal to, say, n from 10 to infinity. So I'm discarding the first few terms. Okay, so if now n is greater than or equal to 10. If n is greater than or equal to 10, then this is greater than sum 1 over 2n squared, right? Square root 2n times square root 2n. So that's sum 1 over 2n, and this is divergent. Okay, so by the comparison test, this is divergent, so your series is not convergent. In fact, your series is divergent at z is equal to 1. Okay, so it converges when z is less than or equal to 1, the norm of z less than or equal to 1, except when z is equal to 1, it diverges. And it diverges for everything else. Okay, so that's one solution. If you remember theorem 3.44. Okay, so it is possible that you are not very familiar with the textbook and you forgot how to use theorem 3.44. Is there any other way to do this? Yes, there is. So theorem 3.44 is the easy way, but of course there is also a hard way. Okay, by the way, some of you only considered when z is equal to 1 and z is equal to minus 1. Okay, and you argue that in this case, you argue that using alternating series test, this is conditionally convergent, but you did not check when z is complex. So for that, I'll have to take some points off. So the grading scheme is the following. So you have the radius convergence. You have 6 points. Okay, so you consider z is equal to 1. You have another 4 points. And then you considered all the z on the boundary. You have another 10 points. Okay, that adds up to 20 points. But if here you only considered z is equal to minus 1, then you'll get 3 points. Okay. All right. Okay, so now let's look at the hard way of doing this. So that's sum z to the n over square root of n plus 1 times n plus 2. So we are looking at the boundary, right? When the norm of z is equal to 1. So if the norm of z is equal to 1, then z can be written as e to the I theta, right? And further, we can assume that theta is not equal to a multiple of pi, right? Because if theta is a multiple of pi, then this is either 1 or minus 1. Okay, so here we only handle complex z. Okay, so now z is equal to e to the I theta to the nth, so that's e to the I n theta. Okay, and then you can decompose this. You can write this as cosine n theta plus I sine theta. Okay. all right, so and then we decompose that into the real part and the complex part. So the plan is to show both converge, okay? So let's first handle this. So use limit comparison. So limit comparison with, say, cosine and theta over n. Okay, so cosine and theta over square root of n plus 1, n plus 2 with cosine and theta over n. So you take limit as n goes to infinity. So this is n over square root of n plus 1 times n plus 2. Okay, so this limit is equal to 1. So either both converge or both diverge. Okay, so that's good, but still we don't know the convergence of this. Okay, so it is not clear whether this is convergent or divergent. So what do? Well, we can use the integral test. Okay, so here integral test. So you look at this integral from 1 to infinity, say cosine x theta over x, right? Dx. Okay, so and then you do a u substitution. You let u equals to x theta. Then this is theta to infinity, cosine u over u, du. Okay? All right. So we still don't know the convergence of this integral. In fact, you cannot, there is no closed form for this integral. Okay? So we don't know the antiderivative of this integrand. But what do we do then? We know that we don't have to compute the exact value of this integral. All we need to do is to figure out whether this is convergent or divergent. Okay, so what we can do is the following. We can use integration by parts. Okay, so integration by parts. So it's going to be, say, sine theta minus theta to infinity sine u over u squared du. Okay? So now this, you can bound it by putting the absolute value. So this is bounded by, so you replace sine by 1. Okay, so this is convergent. Okay, so this integral is convergent. Okay, so therefore this is convergent, and by limit comparison test this is convergent, so that's convergent. Okay, use the same argument. The sine and cosine are basically the same thing, right? The same technique can handle sine and cosine. So by the same argument, this is also convergent, so you add them together, it's still convergent. Okay. All right. So that's that. That's the hard way of doing it. Okay. Next, number 6. So number 6, we have X, a metric space, and we have a function f that goes from x to r, continuous. Okay, so we want to show that the subset of x such that fx is an integer, so fx is an integer, is closed. Okay, how do we do that? Well, first we note that, okay, so maybe it's easier if I draw a graph. So this is x, this is the real line. We have f, right? So we have a bunch of points. We don't know if these are points yet. So, but anyway, so here is some integers, okay? So first of all, it should be easier to see that a union of integers is closed. Okay, so this is closed set. All right, and so this set by definition is the pre-image of those points, right? So those are closed. The pre-image of closed set is closed, right? Because f is continuous. But here, important things to note is that this is not necessarily all of the integers. Okay, that's only part of the integers. Okay, because you can think of the trivial function, say fx is equal to, say, 1 for all x in x, right? So this is continuous, obviously, because it's a constant function, but you see the image of x is only part of the integers. It's not all of it, okay? So that's that. And okay, so next, problem 7. So we have f, a continuous function from R to R. So can there be a bounded closed interval AB such that f of AB is not closed? The answer is no. Or in fact, you can show that the image of a closed and bounded interval under a continuous function is another closed and bounded interval. In fact, I proved this using intermediate value theorem and max-min theorem in the last discussion. So if you go back to check the previous video, then you can see, I think the last 10 minutes I talk about this exact problem. Okay, so that's that. And so for part B, you want to find an example of continuous function from R to R and a closed subset C such that FC is not closed. Okay, so so what are some examples? So here I'm going to present you one. Look at the interval from 0 to infinity. Okay, so this is closed, but it's not bounded. Now consider this function f of x is equal to e to the minus x. Okay, so the image of the interval 0 to infinity under this function is what? Is from 0 to 1. But this is not a closed interval because we can never get 0. Okay, so that's that for the midterm. I think most of you did pretty well. Okay, so if you get your exam and have questions about your grading for problem 3, 4, 5, 6, then just send me an email and let me know. Okay, so now we're gonna start today's material. Okay, so first I want to talk about this problem. So here I have a function f that is real, continuous, So F maps a closed set E to R. Okay, so E is a subset of R, and F is continuous, and E is also closed. Okay, so we want to show that there exists a continuous real function. So that's a function that goes from R to R such that g of x is equal to f of x for all x in E. Okay, so say I have a closed and bounded interval. So that's just one example. Okay, so now I have a function f that's only defined on these closed and bounded interval. Okay, and on those intervals it is continuous. All right, now we have to show we can construct a function g that is continuous globally on R and agrees with f on these intervals. So you can imagine g probably can look something like that. So it's continuous. All right, so you just connect them. Okay, so g is an extension of f. Okay. All right, so how do we construct such a g? So the most naive thing to do is so here you can connect these two endpoints with a straight line, right? Connect them with a straight line, and so on and so on. Then such g is a continuous function, right? Obviously, but you have to prove that. So I'm just going to provide a sketch. So because E is closed, right? So E complement is open. And we know that open sets in R is a countable union of finite open intervals, right? So it's a countable union. Say K from K is in Z. Okay, together with, say, B to infinity and minus infinity at A. Okay. All right, so we know that's the case. Okay. Then we can further assume that the function f is defined, well, in fact, by construction, f is defined at these endpoints, right? Not plus or minus infinity. Okay, so that looks like that. So that's its a. So that's its ak, right? That's bk, right? That's an open interval, and we want to go from here to there. So what do? Well, this is f of ak. So this is f of bk, right? We can define g of x to be this. Okay, so it looks a little complicated. Let me explain what this actually is. So let's see, if you plug in x is equal to ak, okay, let's look at g of ak. So if you plug in x is equal to ak, then this is 0, right? So this term is gone. So g of ak is simply f of ak. Okay, so if you plug in bk, so what is g of bk? If you plug in g of bk, then this is bk minus ak over bk minus ak. So this term is gone. That's 1, right? Then you have f of ak. Sorry, this should be plus. So f of ak plus f of bk minus f of ak. So what's left is f of bk. Okay, so the function g thus defined agrees with f on the endpoints, right? Okay, so between ak and bk, um, this is in fact a linear function, right? Because this is nothing but a number. So this is also a constant number, right? So really this is a linear function because it's of the form kx plus b, right? So k is equal to this and b is something else. Okay, so really what g is doing is connect these two endpoints with a straight line. Okay, now it's left for you to prove that the function g defining this way is actually continuous. Okay, all right. Okay, so next I'm going to talk about the theorem on intervals. It's the characterization theorem of an interval. Okay, so what is an interval? If S is a subset of R that contains at least 2 points and has the property that if xy is in S and x is less than y, then the closed interval xy is in S, then S is an interval. Okay, so if S is a subset that has this property, then S is interval. Okay, so we're going to prove this. We're going to break that into 4 cases. So 1, S is bounded. 2, S is bounded above, but not below. 3, it's bounded below, but not above. And 4, it's unbounded, neither bounded below or above. So here I'm going to prove these 2 cases, and the other 2 cases are left as an exercise. Basically, you can follow the same argument for the first 2. Okay, so let's prove case 1. So here, I'm going to define A to be the infimum of S and B to be the supremum of S. Then, by definition of infimum supremum, we know that S is a subset of AB. Okay, so here we're gonna show, so we want to show the open interval is a subset of S. Then S has to be either this or this or this or this, right? And in any of the cases, S is an interval. Okay, so now if we take a so if we take Z, that's between A and B, so we want to show that Z is in S, right? So what do we know about Z? So we know Z is not a lower bound of S. So there exists an X in S such that X is less than Z, right? So also Z is not an upper bound of S. So there exists a Y in S such that Z is less than Y. Okay, so therefore Z is in the interval xy. Okay, so that property, okay, so that property means what? That property implies Z is in S, right? Because this whole thing is in S. Now, since Z is arbitrary, then we know this open interval is in S. So we have shown that this open interval, then we have shown that S is an interval. Okay, now for case 2, so we can let B be the supremum of S. Then we know S is a subset of that, and we want to show minus infinity to B is a subset of S. Then either S is equal to this or S is equal to that, right? In either case, as an interval. Okay, now if we take Z is less than B, then we want to show B is in S. Okay. So Z is less than B, then there exists X and Y in S such that Z is in XY, right? So XY is in S by our property. So since Z is arbitrary, that shows minus infinity to B is a subset of S. So S is an interval. Okay, that's that. Okay, so next I'm going to show an important theorem called the preservation of intervals theorem. So what does that mean? Okay, theorem that I be an interval and let f be a function from I to R, continuous, then the image f of I is also an interval. Okay, so proof. So because we just seen the characterization of interval theorem, so we try to use that. Okay, so here's the proof. So let alpha and beta be in f of I with alpha less than beta. So what we want to show is alpha beta, this is in f of I. Okay, so if we show that, then we showed this set f of I has the property that we just mentioned in the previous theorem. So f of I is an interval. Okay, so how do we show that? Now, because alpha and beta are both in f of I, right? So by definition, there exists a and b in I such that alpha is equal to f of a and beta is equal to f of b. Okay? Now take any k in the interval alpha and alpha beta, then by the intermediate value theorem, there exists a number c in I with k is equal to f of c. Okay? Now k is arbitrary, so that implies the closed interval alpha beta is in f of I. Okay? So f of I has the property that we just seen from the last theorem. Therefore, f of I is an interval. So this result is really kind of intuitive, right? So you have an interval and a continuous function maps an interval to interval because in a sense you can't have gaps, right? So if the image is not an interval, say like that, disconnected. So there is a gap in between, right? So that will violate the continuity of f, because somehow f has to make the jump from here to there, and that's not possible because f is continuous. Okay, so next I'm going to talk about this concept of uniform continuity. So let's recall the definition of a continuous function. Okay, so f is continuous at set A means what? So f continuous on A means that given any epsilon greater than 0 and u in A, there exists a delta which depends on epsilon and u, such that for all x, such that x in A and x minus u less than delta, we have f of x minus f of u is less than epsilon. So the important thing to note that is delta in general depends on epsilon u. So it depends on epsilon is not too surprising, right? If your epsilon is small, then delta tends to be small too. But the thing is, it also depends on u. Okay, so example. So let's look at the function 1 over x on 0 to infinity. So 1 over x is continuous on this interval, right? But it blows up when x is close to 0. So even though this is continuous, the behavior of this function is not really that good. That's because this delta depends on u. If your u is very close to 0, right? Say this is u. Just change your u a little bit. So there is u plus delta, and this is u minus delta. The function value can change a lot. Okay? So you can imagine if this u is very small, then this delta have to be extra small. Okay, so for uniform continuity is you can find a delta that does not depend on u. Okay, you have a delta, if you give an epsilon, and I have a delta that works for every u, then the function is uniformly continuous. So example, if f of x is equal to 2x, then this function is uniformly continuous because f of x minus f of u is equal to 2x minus u. So if we want this to be less than epsilon, we can simply let x minus u to be less than epsilon over 2. So this can be your delta. As you can see, this delta does not depend on u. Okay? All right. So that's that. And here it's a non-uniform form continuity criteria. Non-uniform continuity criteria. So the following are equivalent. So shorthand TFAE. The following are equivalent. So 1, f is not uniformly continuous. 2, there exists epsilon greater than 0 such that for all for every delta greater than 0, there exists points x sub delta, u sub delta in A such that x delta minus u delta is less than delta, and f of x delta minus f of u delta is greater than epsilon 0. Okay. Number 3, there exists epsilon greater than 0 and two sequences xn and un in A such that limit as xn minus un is equal to 0, but f xn minus f of un, that's greater than or equal to epsilon for all n in n. Okay, so we can see how this works on the function 1 over x. Okay, we can take a to be the interval from 0 to infinity. Okay, so let's look at number 3. So as you can see, number 2 and number 3 are almost the same, right? If this is less than delta, then that means they are close, so their limit is equal to 0, but their function value can be very far apart. So let's consider this function on this interval. We can consider the sequence xn is equal to 1 over n, and un is equal to 1 over n plus 1. Then it's clear that xn minus un goes to 0, but 1 over xn minus 1 over un, this is always equal to 1, right? So their difference does not go to 0. Okay, so now question, how can we quickly know if a function is uniformly continuous or not? So this is a very useful theorem. So let I be a closed and bounded interval, and let f from I to R be continuous on I. Then f is uniformly continuous on I. So in other words, a continuous function on a closed and bounded interval is uniformly continuous. Okay, proof. Say if f is not, then by the previous result, we can find a epsilon greater than 0 and two sequences xn and un in I. So this is un in I such that xn minus un is less than 1 over n, and f xn minus f un, that's greater than epsilon 0 for all n. Okay. Now, since I is bounded, we know both of the sequences are bounded, right? So we know that a bounded sequence has a convergent subsequence. So there is the subsequence x sub nk, so subsequence of xn such that it converges to z. Say it converges to z. Okay. Now, since I is closed, we know that z is in I. Okay. Now, since un, the difference between u and xn is going to 0, so it's clear that you can also find a subsequence of un So let's say u and k, that also goes to z. Okay, so u, because u and k minus z, so that is less than or equal to u and k minus x and k plus x and k minus z. So this is small, right? And this is also small by this condition, okay? So this is small, okay? So that's that. Now f is continuous at z, right? Because f is continuous on I. So we know that this sequence, so this is u and k. So both of the sequence, they all converges to f of z, right? So if they converges to the same thing, then it is not possible. Well, it is not possible because by this, they're supposed to be epsilon 0 apart, but here we just show that they converges to the same thing. So that's a contradiction. So therefore, f cannot be uniformly, then f has to be uniformly continuous. Okay, that's it for today, and I will see you next time.